right, we're live now.
Okay.
Okay, welcome everyone. We're going to have two speakers today. The first speaker will be given by Linda Peteanu, and the second speaker will be given by Chris Vanderwall. And Linda Peteanu is a professor of and the department head of Department of Chemistry at Carnegie Mellon University. Her group studied diverse problems ranging from materials to produce energy-efficient lightning to the properties of our genetic materials, including DNA, RNA, that code for proteins in our bodies. Welcome, Linda.
Thank you. Thank you very much for the introduction and the opportunity to talk to you today. Here I'm going to speak to you about primarily the thesis work of one former student, Woon-Young So, in collaboration with Dr. Rong-Chao Jin, who I believe spoke in your meeting last week. So we're very grateful for that collaboration. All right, so the outline of the talk briefly is I'll introduce the material properties of this class of materials, silicon nanoparticles, that I'll be talking about, and show that the emission that we're speaking about, that we're focused on, is derived from the ligands that are associated with the surface of the particles. My part is primarily the photophysics of these systems, and we'll discuss the fluorescence intermittency and evidence that they exhibit both single and biexcitonic states. And if there's time, I'll speak a little bit about plasmonic effects that, that support our assignment of the single and biexcitonic emission in these systems. So first, in the material properties, so thinking generally about semiconductor quantum dots, in that set of systems, which is most familiar to people, you get very bright size tunable emission due to the quantum confinement effect. However, we know that they contain toxic and costly heavy metals such as cadmium, cesium, lead, and so forth. Nonetheless, they've been very extensively studied, and they're actually one of the first quantum materials to find widespread commercial utility in biological imaging and in displays. So one of the few things that you can actually buy and use. Next generation applications for these systems rely on the idea that they might be useful for solar energy harvesting if you can actually do multiple exciton generation. In other words, with high energy photons, if you can get more than one electron per photon, that will be a very useful property for solar energy harvesting. The materials that I'll talk about today are based on silicon, which is naturally abundant, non-toxic, cheap, and biodegradable. You can ask the question, can some of the advantages and some of the applications that we associate with normal semiconductor quantum dots be done competitively with silicon? So this crowd will know that bulk silicon is non-emissive because it's an indirect band gap material. However, as you make it into a nanoparticle type of system, you increase the emissivity up until about, let's say, 8% for very small particles. And this emissivity, the emission wavelength, is dependent on the core size, with the smallest size having emission around 700 nanometers. By about 5 nanometer particles, you get to about 700-800 nanometer emission, and beyond that, it effectively saturates. So the ligands that are on this surface here are essentially spectators and not really involved in the emissive process. The red emission that you see here is from the silicon core. So remembering these wavelengths, and also that the core emission is weak and red, what I'd like you to do as we go forward. So a number of groups, including Rong-Chao Jin's group, began to experiment with changing the ligands on the surface from more non-emissive or innocent ligands to materials with ring systems. And there it was found that you can go from a quantum yield of 8% up to a quantum yield of about 90%, depending on the properties of the ligands. And moreover, you can tune the color depending on what ligand is chosen. So here you see emission from 3 different ligands that are chosen. You can span the region from blue to orange in this particular case, depending on structural changes. Now, where we got interested here was that we know that this can be done, but it wasn't clear what it was about these structures that gave rise to particular emission colors. So was there any way of essentially predicting what property would give what color, or was it more of a hit and miss? So what I'll back up and just say here for a moment is that we are focusing on the ligands because we recognize that the size of the particle does not impact the wavelength of emission. So this shows two separate preparations using the same ligand with different size distributions, 2.58 and 4.83. Normally, in a core-driven system, there would be a 200 nanometer difference in the emission wavelength here. And what we see is that the emission wavelengths of these two are essentially identical. So this indicates that the core size is not impacting the emission wavelength in these systems. So it further substantiates the need to focus on the ligand properties.
Linda,
What we have found, I'm sorry?
I have a quick question.
Sure.
Those are pretty bulky ligands. Does the amount of saturation on the surface impact the quantum yield?
I expect as you go to very high, you are probably ligand loading, you're going to start getting some self-quenching more than anything else, because you're probably going to have ligand-ligand interactions. These tend to be on order of about 10% of the surface. So there are a number of things on the surface, the ligand being one of them.
Okay, and other stabilizing ligands?
Yeah, and other just oxidation and so forth.
Oh, okay, thanks.
Thanks for that question. So basically, this shows a plot. If you try to look at the emission energy in EVs and you have various ligands that we've abbreviated here, and you try to find any trend, you basically won't find one. And this is the publication, this is summarized. However, if you plot against the calculated ground state dipole moment of the ligand, you get a very nice correlation and a predictive correlation. In fact, we synthesized a new system based on a different ligand just to show, and took other data from the literature just to show that this was actually a good correlation. So it suggests that there is a charge transfer component to the emission the strong emission that we're seeing, and that can be relatively well predicted in a simple way from the ground state dipole moment of these molecules. So that again has already been published. Turning now to the photophysics of these systems, what I'm going to tell you now has primarily been done using confocal fluorescence microscopy, either in solution or as shown here in a PMMA matrix, basically a microscope. It's exciting the sample, collecting the emission, splitting it between two detectors, and you can do both steady state and time correlated single photon counting in these systems. So what has been done in the case of, let's say, cadmium selenide quantum dots as an example, if you look at a single quantum dot, you see what's known as intermittent emission. So you get bursts of emission and then quiescent zones and bursts and so forth. This shows a bare quantum dot. This shows one that's been passivated so that it shows more emission in less dark spots. Now, so obviously at high count, you're getting an luminescence, you create an electron hole that re-radiates back down to the ground state. When you have dark spots, basically that can indicate a number of things. It can indicate energy transfer to a trap on the surface. It can indicate that you have, in fact, formed two excitons and you have an Auger process that's bringing you down to the ground state non-radiatively, or other forms of non-radiative recombination. Once, basically, these will give you a charged crystal, and once you can recapture the electron, you can get the system to re-radiate. So basically, the dark systems are telling you about MEG type processes as well as the presence of traps. So we see very similar type of phenomenon when we look at the silicon nanoparticles. So this is the ones that are 90% quantum yield emitting in the yellow, with this particular ligand combination. So you see these bright bursts of emission, but you also see this kind of low-lying emission here. And so the bright bursts we're going to call the bright states, very imaginatively. And the dim emission here, we also see sort of on all the time. And then the black curve here, the black line here essentially shows what the dark noise of our detector is. So if we sort of separate out by using intensity thresholding, the bright state from the dark state, we see that they have different emission decay dynamics. The bright state decays with the same dynamics that you get for the system in solution phase. The dim state has a faster decay component. So it appears that it's possibly decaying by a non-radiative effect, which is why it shows less emission.
I'm sorry, I have a quick, so it almost looks like there are two time scales, even in the dim one. Like there's something that goes, like there's a really sharp part that's even, like there's a second time scale.
Like an IRF, IRF limited, yes.
Oh, okay,
it is
I see.
exponential.
Okay.
Yeah, and part of this second exponential looks like it's a residual amount of essentially the bright state, because we're doing thresholding, but in some sense,
Okay.
one to the other. Yeah, excellent question. Thank you. So in order, and often I'll point out that when people are using lifetimes, and Jeremy raises a point that's important here, people are using lifetimes to try to determine whether a state is single excitonic or biexcitonic. They're using lifetime curves, but usually you have multiple components, and it's not always straightforward to assign a particular component to a particular physical phenomenon. It's easy if you have a single component, but if you have a multiple component, it gets much harder. So there are other ways of essentially looking at the single versus biexcitonic nature, or the potential for that in these systems, and that's known as using anti-bunching. So this is a methodology, not anti-bunching, but the use of this in assigning biexcitonic states, was essentially pioneered by Munji Bawendi, and basically use the same setup that I talked about earlier, where you have two detectors on which you split the emission. And in one case, the first photon acts as the start photon for data collection, and a second photon that arrives acts as the stop photon. Now, what the data ends up looking, if you have pulsed excitation, which is what we have a laser pulse that's about 100 picoseconds long, and it's has its repetition rate in the 40 megahertz range or so, is that you'll get a burst of emission every time that basically you have two sequential absorption and emission events. So a photon is absorbed, emitted at the repetition rate. But at the center here, where the time delay is zero, you'll get essentially zero intensity here if it's the case that the molecule cannot absorb and emit a photon within the laser cycle. It cannot do that more than once. So most single molecules will show what we call high contrast or no intensity here, because they cannot emit two photons within one laser cycle. Okay, and if you can emit two photons within one laser cycle, you will show intensity here. And so the ratio of the ability of the center intensity here to the side wings gives an idea of the biexciton versus exciton quantum yields, because only in a biexciton state where you have two excitations present can you expect to see two photons come out simultaneously from the sample. Okay, so that's the basic idea of that type of measurement. What do we see? So if we threshold this dim emission that I'm pointing to here and this bright emission, and we measure the second order photon correlation, if we measure it overall, we get kind of a mixed case. This is the sideband peaks that I talked about that are large, and then this is the center peak at time equals difference in time between the two detectors equals zero. But if we do the thresholding, we see that the bright emission essentially shows no intensity here, whereas the dim emission shows relatively high intensity here. This shows that these two types of emissions have very different photon statistics, which suggests that they arise from different states within the molecule, and furthermore suggests that the dim emission has a biexcitonic character as per the analysis that Bawendi has developed. So we can also show that by looking more sort of conventionally at what these emissions look like. So this is we took the emission from a single particle here, and we dispersed it such that we have the emission of a single molecule, a single silicon nanoparticle, and it's superimposed on the bulk emission spectrum. And once you look at a single molecule, you can see some of the finer details. And one of those finer details is an emission bump at about 625, which is rather small compared to the main feature. But the main feature, again, is a really high quantum yield. This is the ligand-derived emission, and its quantum yield is about 90%. But this is a reproducible small feature in the region that others have assigned to a biexcitonic band within a silicon nanoparticle that does not have emissive ligand states. And so if you do photon statistics in solution of the type I just talked about, and you wavelength select, say I'm only going to look at the emission from this state, I get a pretty high contrast between, and relatively little emission, relatively few counts at t = 0, or high contrast anti-bunching. If I focus only on this region with a filter, I essentially get almost equal intensities between these bands, showing a low degree of anti-bunching, a high degree of biexcitonic character. If I do the, plot it as a function of wavelength, I can see that the emission intensity, the biexcitonic character, increases to the red, as I would expect for something that's derived from the silicon core and shows this biexcitonic character. Just say in 2 seconds, 2 minutes rather, sorry, other ways in which we can think about how we can support this assignment. There have been a number of reports in the literature that interaction with gold surfaces can cause semiconductor quantum dots to show preferentially biexciton and multi-exciton emission versus the same properties on glass. And so we effectively did that experiment ourselves with a thin gold film and our nanoparticles there. This shows the overlap between the plasmon of the particle of the gold film and the emission band that we ascribe to the biexciton. And this shows another photon trace where now one can see that the dim emission is enhanced on gold versus on glass. And there's a quenching of the bright emission here. And that's also seen where basically this bright emission band here is quenched when we go to gold, and the low intensity emission is enhanced. Finally, we can do the same experiment comparing gold to glass, and again thresholding bright versus dim. And once again, we find that there is an enhancement of the or a decrease in the anti-bunching contrast on gold rather, which signifies that we have enhanced the biexcitonic emission compared to single excitonic emission. And once again, if we look at the lifetimes, what we see is that the lifetime of the biexciton state has gotten even shorter. So we presume from this that the plasmonic surface is enhancing the biexcitonic emission because it's increasing its radiative rate and making it competitive with the factors that will cause it to be quenched, whereas the single exciton state is quenched by energy transfer to the surface. So to conclude, basically the emission wavelength of the silicon nanoparticles can be tuned in a predictable way by changing the ground state dipole moment of the surface ligand. Biexciton state emission can be clearly identified by photon correlation measurements and can be enhanced by plasmonic interactions, which can also be used to identify it. With that, I'd like to thank primarily the student who is now a postdoc at the NIH who is involved in this work, Rong Chao Jin and his group for an excellent collaboration, and the National Science Foundation for their support, and you for your attention and invitation. Thank you.
Okay, thank you, Linda. Thank you. There's one question for you from a YouTube audience.
Oh.
Okay, this question referring to slide 14.
14, okay, let me get that.
Okay, would you move to slide 14?
Oh, sorry.
14.
Yeah, I'm trying.
4.
Getting there. I apologize. It's a little slow. Okay, yes. I'm on
Yes,
board.
okay. Now, does the lifetime curve below a bi-exponential or a stretched bi-exponential curve, which of these will be the better to fit data in this nanoparticle system?
Good question. We have found we can fit it. I tend to not fit things with a stretched exponential if I can fit it with 2 or 3 exponentials. I don't think that there is anything really that's physically achieved by fitting it as a stretched exponential. So we have fitted as, I believe it was a bi-exponential in this case. And what we found is that your dominant decay is this IRF limited, very fast process. And then there is a component which is essentially like that of the bright state emission. There are sometimes additional components, longer components that you can get, which we don't ascribe too much meaning to because they're very low intensity. But I don't see any reason why you wouldn't be able to also fit it to a stretched exponential.
Okay, thank you, Linda. Because of time limit, we'll have to move on to the next speaker. Thank you, Linda.
Sure.
Okay.
I share.
Yeah, we just share the. Okay. Our next speaker is Chris van der Waal. Professor van der Waal is a distinguished professor of materials and Herbert Kremer Chair in Material Science in the University of California at Santa Barbara. His research interests lie in novel electronic materials and energy storage. He studies wide bandgap semiconductors, including 3,5 group nitrides, 2,6 group compounds, and complex oxides, with applications in solid-state lighting, photovoltaics, and high-power electronics. Van der Waal investigates the interplay between structural and electronic properties of surfaces, addresses problems related to doping and defects, and investigates loss mechanism in light emitters. Okay, Chris.
Okay, thank you for the introduction, and thanks for the invitation. I really appreciate being able to talk to you today about our work in modeling point defects for quantum information science. On the first slide here, I acknowledge a number of people who've been instrumental in doing this work. In particular, I'd like to acknowledge David Avshalom for initially getting me interested in this problem, particularly in the context of the NV Center in Diamond. I'd also like to acknowledge the support of NSF and DOE. So in the context of quantum information science, people talk about qubits and single photon emitters, and essentially these are centers in which you have a single spin, or where you can emit a single photon in a particular well-defined quantum state. And that allows you to create, control, and manipulate novel classical states of light and matter, and basically enables applications that you cannot perform classically. So those include applications in quantum cryptography, in imaging and sensing, and of course in quantum computing. So even for the qubits, since manipulation of these centers often involves absorption or emission of light, it is really essential to understand the fundamental concepts related to light absorption and emission. And that's what we've been trying to do in the context of our first principles calculations. And actually, as you will see, that also allows us to elucidate some basic principles about how these centers operate and how to control them. So if you want to create, let's say, a qubit, we can think of like an atomic structure with a single spin, and that could be like a hydrogen atom as a prototype. But of course, a single atom suspended in free space is very difficult to control. People manage to do that, for instance, trapped ions or molecules, but in general, embedding this single spin center into a solid state environment allows you to have a lot more control. So that's the idea of using quantum wells or quantum dots, or using point defects, very often referred to as color centers, which was kind of the original term used for point defects in alkali halides. And these are, for instance, vacancies, missing atoms, or impurities in materials that have a band gap, semiconductors or insulators. So this then gives you a solid state system where quantum information can be manipulated, preferably at room temperature. Okay. As already mentioned, the prototype of this is the NV center in diamond. Now, the advantages of the solid state system are, of course, greater control, but also it gives you access to widely available fabrication tools. It's easier to connect to classical measurement and control systems. The whole system becomes a lot more robust. Solid state systems lend themselves to miniaturization. Think about the whole silicon technology infrastructure that you potentially could tap into. And of course, along with that is scalability. So I mentioned the NV center in diamond, and quickly I want to go over that. So that's basically a missing carbon atom in a diamond crystal. And the N stands for nitrogen, a nitrogen impurity embedded in that crystal next to the vacancy. Okay, so this forms a defect. It's actually a complex with many desirable properties. Okay, it can be used as a qubit. It operates at room temperature. It gives you an optically addressable single spin, as we will see. And in terms of controlling that spin, coherence is, of course, very important. And for the NV center in diamond, millisecond coherence times have been demonstrated, which is essentially an eternity almost in terms of being able to manipulate those spins for actual quantum computing applications. So this is all extremely promising. Except for the fact that diamond is, of course, a very difficult material to work with. It's difficult to grow, it's difficult to process. Natural diamond is very expensive. So from the early stages of investigations of this center, the question was raised whether similar defects could be identified in more technologically amenable and mature materials. Okay. And in order to address that question, 10 years ago, we tried to propose a set of physical criteria that should be met by the host material and the defect in order to form a suitable single spin center. And I won't go through these criteria in any detail, just kind of mention the broad points. You would like to have the host material to have a wide band gap, so that the states induced by the defect, as is illustrated here for a vacancy in diamond, are located nicely within the band gap. There is minimal coupling to the valence band or the conduction band. You would like to have a material in which spin-orbit coupling is small, because spin-orbit coupling can give you unwanted spin flips and a loss of coherence. That then relates to the fact that the constituent elements, if possible, should have zero nuclear spin to avoid interactions with nuclear spins that can lead to spin flips. And of material should be able to be grown high quality in thin films be experimentally feasible to create and address individual defects. So in the ground state vacancy in diamond, if you think about it, you've removed the carbon atom, you have 4 broken bonds, each of which now has an unpaired electron, so you have a total of 4 electrons. You occupy the levels I sketched here for this vacancy diamond with these 4 electrons, find this occupation, which corresponds to 0 spin. So for quantum application, this is not particularly interesting. Now, if you put a nitrogen atom to, you can see nitrogen has valence 5 instead of carbon valence 4. So you get an extra electron, and that electron goes into the next state here. So you actually have a spin 1/2 system, which could potentially be interesting. But as we will see in a moment, the most widely used occupation of states corresponding to the charged state is defect, is the charged state, in which you bring in an additional electron. So this second E state within the band gap gets occupied, and you get a spin state. And it turns out that for applications, this is the most desirable configuration. So what I'm showing here is that, of course, there is a direct coupling between the occupation of the states in your defect center and the charge state of this defect. And that's something we're going to be talking about as an important criterion for designing such defects. Okay. So in the process of doing that, as I said, we developed a set of criteria, and then to evaluate those criteria, we can actually use first principles calculations and build on the capabilities in that area to help analyze and design defects. And these tools are based on density functional theory, hybrid functionals, sometimes using many body perturbation theory as needed. So I talked about the importance of the charge state of the defect. And very often we use diagrams as the one illustrated here to investigate these issues. What is plotted here is the so-called formation energy of a defect, how much energy it costs to, for instance, create this NV center in a diamond host. And it is plotted here as a function of the Fermi level in the material, the electron chemical potential, which ranges from the valence band at 0 to the conduction band at the value of the band gap of diamond. On the left-hand side, we would have P-type material, acceptor doped material. On the right-hand side, we would have N-type material, donor doped material. So as I was saying earlier, to get the optimal spin state of the NV center, we want to be in the -1 charge state. Now, in general, it is actually not so straightforward in a semiconductor or insulator to select Fermi level positions that lie within a certain range within the band gap. It is relatively easy to dope the material fully P-type with the valence band close to, with the Fermi level close to the valence band, or fully N-type with the Fermi level close to the conduction band, but intermediate Fermi levels can be difficult to achieve. In the case of the NV center in diamond, we are actually lucky. Maybe this is actually one of the reasons for the success of this center. Because if you look at other centers or impurities that are commonly occurring in diamond, well, you can look at vacancies, but actually, even in natural diamond, nitrogen is present in fairly large concentrations as an impurity. And of course, that's also why you have these nitrogen vacancy centers. And it turns out if nitrogen is the dominant impurity, then the Fermi level will be determined by this dominant impurity. How is the Fermi level determined? It's basically determined by charge neutrality, okay? Overall, macroscopically, our material needs to be neutral. If you put a large concentration of nitrogen in the material, larger than any other defect or impurity, then the level position is going to be determined by this nitrogen substitutional impurity, which could be positively charged or be neutral, or it could be negatively charged. Now, in order to guarantee overall charge neutrality, the vast majority of the nitrogen will need to be in the neutral charge state. And as you can see, by coincidence, or maybe not, the Fermi level gets located smack in the middle of this green region where the NV center is in the correct charge state that gives us that spin 1 state. Okay, so that's a fortunate event in diamond that gives us that correct charge state. Once we have the correct charge state, the correct spin state, we can look at optical excitations. Okay, and in order to analyze that in detail, I won't go into that in this talk. You actually look at multiplet states, but the basic issue is that you use light, absorption of a photon, to excite an electron out of this ground state level into an excited state. Okay, and that takes approximately 1.9 electron volts. During the excited state, the electron can come down again to the ground state. These transitions, these optical transitions of absorption and emission, are spin conserving. Okay, but once you're in the excited state, there is actually also a non-radiative channel available where the spin flips. Okay, this is what I mentioned before, that spin orbit coupling, etc., is very important. So if you get into that non-radiative channel, then the electron goes down to the ground state, not by emitting photons, but by losing energy through lattice vibrations. This is referred to as the intersystem crossing. So I won't go into detail about this, but just show this to illustrate the importance of understanding how radiative and non-radiative transitions occur in these centers, because that allows us to calculate rates for these processes and calculates and allows us to decide how to optimally manipulate and control the center. Okay. So because of the importance of the optical excitations, people have, of course, done lots of optical experiments. This is a photoluminescence spectrum for the NV center in diamond, and I will come back to that a little later. So in the next part of the talk, I want to briefly discuss these issues of radiative and non-radiative recombination, talk a bit about the physics of it, and illustrate how, with first principles calculations, we can actually explicitly calculate these relevant rates. Okay. As I already mentioned, you can either have radiative or non-radiative recombination. This is illustrated here with the example where you would have a defect level in the band gap that can have different charge states. You have, for instance, electrons in the conduction band. Those electrons can lose energy by going to an empty state in the defect level, and the energy can be lost in terms of emitting a photon or through lattice vibrations, phonons. Let's first talk a little bit about radiative recombination. Okay, and I wanted to choose a specific example which we've kind of used as a benchmark because it has been so well studied, and it also illustrates the power of doing these calculations for actually identifying the source of optical emission that is experimentally observed. Okay, my example is carbon in gallium nitride. 40 years ago, there were already experiments that showed that in almost all gallium nitride, you see yellow luminescence, a broad luminescence band centered around 2.2 eV that is almost universally present. And there were hints that this was related to the presence of carbon in the material. But for the longest time, basically until around 2010, there was no good explanation for what the microscopic center was that was actually causing this emission. Of course, it's tempting to think that it could be just a substitutional carbon impurity, but the information that was available about carbon seemed to conflict with giving rise to yellow luminescence. So what we did was a systematic analysis of carbon. And for the optical transitions, what you want to do is create a so-called configuration coordinate diagram. You look at the two possible charge states that are going to be involved in this transition. Let's say that the negative charge state is the ground state. If you lift an electron out of this carbon level by exciting it with a photon, you can put it into a neutral charge state plus an electron in the conduction band. And as I said, that involves absorption of a photon. And then once you're in that neutral charge state plus the extra electron, you can go back to the ground state by letting the electron drop down again and letting the carbon become negative again. And that, of course, will be accompanied by emission of a photon. Now, in this diagram, it's already clear that you're going to have a so-called Stokes shift, a frequency shift between absorption and emission, because these processes occur on a time scale faster than the time scale on which atoms can move. So these roughly parabolic curves, these configuration coordinate curves, illustrate how the energy of the center changes as a function of the coordinates of the atoms, the carbon, and the surrounding atoms in the gallium nitride crystal. And of course, you start out in the minimum of the curve, but when you absorb a photon, the atoms basically don't have time to move on that time scale. So you end up in the state for the neutral carbon that is not actually the lowest possible state. And then on a longer time scale, you get down to the minimum. Once you're in the minimum, you emit a photon, and that's going to occur clearly at a much lower energy or a much lower frequency. So we can now model all of these things with first principles calculations based on density functional theory. This is a formation energy diagram again, in which you can recognize this neutral charge state, negative charge state. Here's the configuration coordinate diagram, but now based on actual calculated numbers. And to make a long story short, here you see that we expect the emission to occur preferentially at an energy of 2.14 eV, which is basically smack at the center of that yellow luminescence. Okay, so this is basically conclusive proof that simply a substitutional carbon atom in gallium nitride gives you that yellow luminescence. The microscopic origin was elusive for a very long time. Okay. So far I focused on like what the most likely optical transition process is by looking at these vertical transitions. As I mentioned, in the case of yellow luminescence, the emission is actually broad, and that can happen because you can have transitions not just for one particular atomic configuration, but at a finite temperature or even at zero temperature. Because of 0-point motion, the atoms are always moving, and that's going to lead to a broadening of the line shape. which we can actually also explicitly model from first principles. Okay, so here are some examples of doing that for various defects in gallium nitride, and comparing theory, the solid curves, with these digitized curves for experimental measurements. You see that there is remarkably good agreement for most of these defects for the computationally predicted luminescence line shapes to agree with the experimental line shapes. Okay, so if this is for a known defect, you can say, well, so what? But very often in optical experiments, emission lines and line shapes are observed, the origin of which is not a priori clear. And this illustrates that first principles calculations can be very powerful in helping identify the origin of such luminescence. So just to return to the NV center, we've done this sort of calculations also for the NV center in diamond. Here's the configuration coordinate diagram. We can calculate absorption and emission energies, and we can actually also calculate the luminescence line shape, which is quite difficult in that case. My collaborator, Aldrius Alkauskas, did a great job on this. And as you can see, you can actually model the line shape quite well, including all these intricate oscillations that are observed due to interactions with specific phonons. So in the next few minutes, I want to tell you a little bit about non-radiative recombination. Okay, so the radiative recombination in configuration and coordinate diagrams such as this one involves these vertical transitions that are induced or involve photons. Non-radiative recombination does not involve photons. It involves going from one state of the defect to another lower energy state of the defect, essentially by crossing over from one curve to another using energy available in the lattice. And if you think about this semi-classically, you would say, well, okay, all I need to do is go over an energy barrier to be able to get to this lower energy curve. But of course, nature is not classical, nature is quantum mechanical, and that means that simply using these classical barriers is actually not very accurate, but we can calculate the actual rates with which these transitions happen really based on quantum mechanical principles. So I'll just flash the equation for the rate that we use. You will recognize that this rate is basically an expression based on Fermi's golden rule. You see a matrix element squared, and you see, well, maybe not directly, but there is a density of states there, which comes about because of energy conservation. There is a delta function that says that the energy in the system needs to be conserved. The energy of the initial and the final states need to be the same. And if you integrate this energy delta function over all possible states of the system, you essentially map out the density of states. So this is Fermi's golden rule, and the quantities that occur here can be explicitly calculated from first principles. The electron-phonon coupling, the band structures, and the phonon properties that give these energies, etc. Okay, so again, for my example of the carbon in gallium nitride, we can actually, in addition to analyzing the radiative transitions, also analyze non-radiative transitions. And this is a capture coefficient that describes the rate at which holes would be captured. And the calculated value, which is plotted here as a function of temperature, agrees remarkably well with the experimental measurements that were performed within this temperature range. So again, this serves as a benchmark to show that we can actually calculate these non-radiative rates in this case with high accuracy. Okay. So that's kind of our toolbox. And in the last few minutes, I just want to briefly mention how we have applied these tools to start exploring other defect centers in other semiconducting or insulating hosts that might serve as qubits or single photon emitters. Okay. The first material we looked at after diamond was silicon carbide, because it is still a group 4 material, and you can actually form centers there that are similar to the NV center in diamond. The main difference in the case of silicon carbide is that the band gap is smaller, and that actually also means that the transition energies for these optical transitions are lower, and actually the transition turns out to be around 1 electron volt instead of around 2 electron volts, and that could be advantageous, for instance, if you want to move closer to telecom wavelengths and take advantage of the infrastructure associated with that. The next set of materials we've been looking at are 3 nitrides. Gallium nitride, widely used for light emitters and also for electronic devices. And if you want an even wider bandgap, aluminum nitride, bandgap of 6 electron volts, where we've explored a number of possible defect centers, for instance, nitrogen vacancies, but we've actually found that complexes between those nitrogen vacancies and transition metal impurities could be very attractive for single spin centers. And we know that some people are actually experimentally pursuing this and have shown preliminary, very promising results. Okay. So finally, I want to mention 2D materials, okay? Layered materials, which have been flagged as being very attractive for quantum applications, because kind of by definition in these layered materials, defects would be close to the surface, which could be very favorable for control. It can also be very favorable for sensor applications, okay? And because the surfaces of these 2 materials are relatively inert, having a defect close to the surface is actually much more acceptable than it is in the case of diamond, for instance, where the surface can actually serve as a source of decoherence. So in this context, hexagonal boron nitride has turned out to be a very attractive material. Already a few years ago, it was demonstrated that very bright light emitters occur in hexagonal boron nitride that emit photons, but can actually emit photons in a controlled manner in the form of single photons, which would be very attractive for quantum applications. Okay. There are actually 2 sets of emitters, one centered around 2 electron volts, the other centered around 4.1 electron volts. For both of these, the microscopic origin has been elusive. There have been lots of proposals, but no conclusive experimental identification. And we thought this was a nice opportunity to put our computational tools at work to help identify this microscopic origin. Okay, so I'll just conclude with showing what our proposed candidates are. For the emission around 4.1 eV, what we are proposing is a pair of carbon atoms. Carbon is always present in hexagonal boron nitride as an impurity. This center, which is essentially a combination between a donor and an acceptor, has quite a low formation energy. It's quite likely to occur in the material, and it actually turns out to have properties that are very close to what is experimentally observed for this 4 eV emitter. So that was documented in the paper I'm flagging here. For the 2 eV emission, what we're proposing is dangling bonds. Now, dangling bonds are usually considered as defects that you want to avoid. In silicon, they mess up the electronic behavior of the material. You need to passivate them, you need to suppress them. In hexagonal boron nitride, we think they are quite likely to form, for instance, near the edge of the flakes that are usually studied experimentally. And if we study their optical properties, they are very close to all the properties that are observed experimentally for the 2eV emitters. Okay, and again, we use configuration coordinate diagrams, we analyze radiative and non-radiative rates, and it's all extremely close to the experimental observations. So I think I'm out of time. I will just leave my summary up here, and hopefully we'll still have time for some questions, which I would be happy to answer. Thank you for your attention.
Thank you for a nice talk. Okay, so we have some time for questions. Any questions from audience?
Oh, okay, me.
Yeah.
Hi, Chris. Very nice. So midway through the talk, we first spoke about calculating the Stokes shifts on, I think it was a carbon-nitrogen system. Do you need to somehow optimize the excited state geometry to know what displacement needs to be? And then does your fitting of the phonon spectrum essentially then consistent with the the Huang-Reis factors that you expect? I mean, is that progression? What is the configuration coordinate here?
Yes. So thank you for bringing that up. The geometry is explicitly optimized both for the ground state and for the excited state. The variation of energy with the displacement of atoms is explicitly calculated. That allows us to calculate the vibrational properties of the excited state, which may be similar to that of the ground state, or they could be different, but that's fully taken into account. And then, well, for this talk, I actually took out several slides that described how we actually calculate the line shapes, which of course involves also identifying the Huang-Reis factor, which tells you essentially the amount. It's some measure for the amount by which the lattice relaxes differently in the excited state versus the ground state, how big the relaxation energy is. And again, in the cases where we've done our benchmarking, where those Huang-Reis factors have been experimentally determined, our calculated values are very close to the experimental values. We have actually also used that in our identification of these centers in hexagonal boron nitride that I talked about. The Huang-Reis factor has been experimentally measured for those centers. We can calculate it, and for the centers that I proposed, the agreement is very good.
So it seems like there's a pretty huge distortion of the lattice given the size of the Stokes shift that they're measuring. Is that right?
That is right. For these examples of defects and impurities in gallium nitride, invariably we find very broad line shapes, large relaxation energies. For quantum emitters, such large relaxations are typically not desirable. You actually want a small Huang-Reis factor. And I think for both the centers in hexagonal boron nitride I talked about, the Huang-Reis factor is smaller than 2. So that's a good sign for those defects.
Okay. Jeremy, you have a question?
Yeah, thanks for this talk. Very, very thought-provoking and exciting about the future in this area. So, I mean, I have a few questions. So, I mean, you can choose which ones you want to answer, but they're kind of, in some sense, related to one another. So, I mean, as you expand out into new materials, so from the initial experiments were done in diamond, and they have certain properties like room temperature, but they have like fixed parameters. And you mentioned that some of the advantages of looking to new materials might be that you can, for example, go to telecom wavelengths. So that they may be more amenable, they may be more tunable. But I guess the question is, in that regard is, are you what about other aspects that have to do with, for example, the relationship between defects? So if we think from quantum information, science, we don't care just about single qubits, although if you're doing sensing, maybe you only care about a single qubit. Is it possible to create less stochastic arrangements of these, and maybe like have regular networks, or be able to control them on size scales that might be integratable with nanoelectronics, for example? What is the prospect for that?
Oh, that's very exciting, and well, it's really more of an experimental issue than a computational issue. On the computational side, because our calculations are very CPU demanding, going beyond the modeling of a single defect would be very difficult. Explicitly modeling even the interaction between two defects would be difficult. If we wanted to address that, what we would do is calculate the relevant parameters for a single defect, and then use other type of modeling to use those parameters to figure out how defects interact. But on the experimental side, great progress is being made in actually controlling very precise positioning of point defects. That can be done, for instance, by specific implantation procedures. I didn't talk about it, but the NV center in diamond is typically created by having a nitrogen-doped material. So the nitrogen atoms are already there, and then doing irradiation or implantation that creates damage, that's going to create the vacancies, and some of those vacancies will be next to a nitrogen atom. Now, you can do the implantation essentially with almost nanometer size control by using very narrow beams or templates, masks. So that can be done with very high precision. And I don't think we're yet to the point where you can say, well, I want one NV center here and the other NV center 10 nanometers apart. But through a process of like trial and error, at least some samples can be identified in which this can be accomplished. And the same implantation procedure could also be used and is being used, for instance, to implant transition metal impurities or rare earth impurities and put them at very specific positions at predetermined distances from each other to study and hopefully exploit their interaction. Another approach would be through growth, which, I mean, this is a slightly different area, but the work on spin centers in silicon, for instance, phosphorus donors in silicon, in which the group in Australia, led by Michelle Simmons, is a world leader. It has demonstrated that you can actually position these phosphorus atoms with atomic precision. In that case, you use a scanning tunneling microscope to basically put your phosphorus atom down exactly in the atomic position that you wanted. And then again, creating pairs or arrays can be done in a similar fashion with exquisite control.
Yeah, so I mean, so in all of these cases, though, well, either you have the naturally occurring defects, or it's top down, which again, because of this, the atomic precision, I mean, it is very hard. I mean, low temperature STM method is, it's kind of hard to imagine, you know, scaling it up to thousands or, you know, hundreds of thousands of qubits of spin. But so I guess the question then is there room for a synthetic route, and maybe one that could be predicted by, you know, ab initio calculations? Are there routes where you can design precursors or something that could lead to these types of spin defects, but they're not, we wouldn't call them defects, they would be, you know, like something you meant to do, but it would have the properties that you're trying to, you know, discover in these defects, but they would be engineered somehow, or maybe, you know, synthetically or synthesizable.
One example comes to mind where you would start with a substrate of your host material that has a slight cut. And if you have a slight miscut, as you know, you're going to get steps on the surface, and depending on the angle of the miscut, the distance between the steps can be very accurately controlled. So at least in that one dimension, you have the opportunity of positioning impurities, for instance, which tend during growth to stick to the step edges. And that's actually something that could be studied computationally. What is the binding energy between an impurity and a step edge? Will the impurity really want to go there? But if it does, that gives you an opportunity, at least along that one dimension during growth, to do controllable positioning. What happens in the other dimension along the step, you would still need to figure out, but maybe there would be enough coupling already that there is a tendency for things to line up. But that's one example that comes to mind. I think that addresses what you were thinking of.
Well, it's the square root of the answer, but yeah, I mean, so like, I mean, like, I don't know about all these, but like metal organic frameworks, they're like these, you know, nanometer scale arrangements where like maybe there's a way to, you know, to have a 2D nucleation, like you're saying, or even it be part of the structure. Like, I don't know. I'm just trying to see. I mean, the 2D material front is really very interesting because there's so much growth in properties of these materials, and then the ability to connect them to the intrinsic properties of the 2D materials, right? And here we're playing with, you know, it's like the hexagonal boron nitride is like playing with the box, you know, that something came in, right? But there's like all these other materials, right? They all can have either be close to defects, so in which case they would interact, or they could be the defects themselves. I mean, so I don't know. It just seems like a really wide open field. So it's
it definitely is. I will share with you my preference for working with materials for which there is a technological base available. You're speculating about metal organic frameworks. Sure, in the context of other non-electronic applications, those materials are already widely used. But I tend to think that quantum information applications are closer to electronic and optoelectronic devices. And those are the sort of materials and devices that ideally you want to be able to couple to do the intricate classical processing that you will need to do something with the quantum information. And so if we can come up with a system that works within silicon technology or gallium nitride, or these days, gallium oxide, which is rapidly being developed into a technological material, has a wide band gap. It's excellent for high power electronic applications. So there is a big drive from industry to develop that material. And it has a band gap of close to 5 eV, which is almost the same as that of diamond. So if you can find a good defect center with single spin or single photon emitting properties in such a material that directly couples to semiconductor technology, that would be my preference.
No, I mean, that's a really good point. I mean, you could argue that we're still in this, like coming out of the starting gate, right? And so working with silicon would be great, and the phosphorus donors, that would be great. But even these emerging technologies, and I think there are people who feel like 2D materials are, might be the, emerging technological materials, even though they're not at the moment. They're still, Scotch tape level technology. But it's, that's also, I mean, thinking forward, if things move in parallel and there is enough promise for 2D materials, then they could be considered to be, the materials of the future, right? That it's okay to think about having an industrial process that involves them. But I mean, like graphene, the wafer, like large scale sheets of graphene that can be grown and so forth. But yeah, I mean, I agree that the more mature the technology, the more the base you can that you can work off of, the easier the hardest problems are going to be. So yeah, this is really inspiring though, to see all this progress.
Okay, I think we used all our time, and we reached the time limit. So I guess we have to close our session. So let's thank our two speakers for their great talk again. And see you next time. Okay, say bye-bye.
Yes.
Thank you. Goodbye.
Thank you, Chris. Thank you, Linda.
So are we still on?
Yeah. I'm not going to stop the stream. I mean, I'll edit it later.
No, but I mean, we're not broadcasting, all right?
Yeah, we are.
Okay. Hello, world.
After we can stop broadcasting.
Well, probably.
All right.